We are surrounded by AIs that talk, that answer, and, they seem to think. Just in the last couple of years, it feels like the sophistication has just exploded.
It really has.
But this brings up a really classic question. What does it actually mean for a collection of, circuits and code to have intelligence? And how do we even start to test for that?
It's the ultimate measurement problem, isn't it? Today, we're taking a deep dive into those classic definitions of machine intelligence. We're going to start with the foundational test from decades ago,
Okay.
and we'll compare that theoretical standard to the huge philosophical challenge it immediately provoked. And then we'll look at where modern AI is today, from these really sophisticated illusions of consciousness to, actual security threats.
And our sources for this take us on a really fascinating journey. We'll be looking at the behavioral standards set by Alan Turing, the philosophical challenge from John Searle's Chinese room argument, and then we'll get practical.
Yeah, with things like CAPTCHA.
Exactly. How systems like CAPTCHA have become these little involuntary Turing tests that machines are now just passing with ease.
We're moving from the abstract to the real-world application. And what you find is that the philosophical questions that were raised 70 years ago, they are now driving the very real security challenges we all face every single day.
Okay, so let's unpack all of this. Let's start right at the beginning, at the genesis of the whole idea, the imitation game. So back in 1950, Alan Turing, who is, the father of theoretical computer science,
Right.
he proposed a way to get around that really frustrating question, can machines think?
Yeah.
He basically said, let's just replace it with a practical behavioral test.
His argument was, look, if it acts intelligently, we should just treat it as intelligent. And that idea became the Turing Test, or, the TT.
And the original concept was so simple, this exercise he called the imitation game.
It was beautifully simple. Picture three people, player A, player B, and an interrogator who is player C. And the communication between them was strictly limited. It was all typewritten answers, like on an old teleprinter.
And that was on purpose, right? To stop the tone of voice or anything physical from influencing the judge.
Exactly. No tells. And the interrogator, player C, had one simple goal: figure out which of the other two players was the man and which was the woman.
Okay, so far so good. Where does the machine come in?
This is the genius move. Turing asked, okay, what happens if we swap player A, the man, with a computer?
Ah, I see.
If that machine is programmed well enough that the interrogator mistakes it for a human as often as they would mistake one human for another, then the machine is considered intelligent.
So it's completely external. It's only focused on the conversational output.
That's it.
And Turing was really optimistic about the timeline for this.
Wildly optimistic. He famously predicted that by the year 2000, computers would be so good at this imitation game that the average person interrogating it wouldn't have more than a 70% chance of getting it right.
After just 5 minutes of questioning.
After just 5 minutes.
Yeah.
The core philosophy here is strict behaviorism. The TT doesn't care how the machine gets there.
Right. It's a black box.
Exactly. It doesn't care about the internal state. If an agent is behaviorally indistinguishable from an intelligent agent, then that behavior is your benchmark for intelligence, the mechanics inside. For the test, they're irrelevant.
But that reliance on pure behavior is exactly where things get really interesting. It's what caused the first major philosophical earthquake in the AI debate. So here's where we get to that fascinating counterargument. The Chinese room argument, proposed by the philosopher John Searle in 1980.
And the Chinese room, or CRA, it directly attacks the whole philosophy of the Turing test. It asks, can just running a program, a piece of software, ever create real understanding? Searle called the claim that it could strong AI.
Okay, so walk us through the setup of the Chinese room. It's a thought experiment, right?
It is. Searle asks you to imagine him or, anyone who doesn't speak a word of Chinese locked inside a room. Through a slot in the door, he gets slips of paper covered with Chinese characters. These are the inputs, the questions.
Right. And he has no idea what they mean.
None at all. But inside the room, he has a massive manual, a huge instruction book written in English, and this book is the program.
So the book has rules like, if you see this squiggle, write down that squiggle.
That's exactly it. He's not reading, he's not translating, he's just following these formal rules based on the shapes of the symbols. He's doing computation.
He's correlating input symbols with output symbols based on their syntactic shape, and then he sends the answers back out.
He does. And from the outside, the answers are perfect. They're coherent, they're timely, they're completely indistinguishable from a native Chinese speaker.
So the room passes the Turing test with flying colors. But if we open the door,
We find Searle, the operator, who understood absolutely nothing of the conversation. He was just manipulating symbols without any grasp of their meaning. He had the syntax, but absolutely zero semantics.
okay, that distinction, syntax versus semantics, is so key, but it can sound a bit academic. What does that mean for you, the listener, in plain terms?
It's the difference between moving a chess piece according to the rules and actually understanding the concept of checkmate. Syntax is just manipulating symbols by their shape, the rules. Semantics is the actual meaning, the comprehension.
I see.
So Searle's narrow conclusion is that just running a program, a set of formal rules, can never produce genuine internal understanding.
But I can argue, look, if the output is flawless, who cares about the internal black box? If it walks like a duck and talks like a duck, isn't that just being a bit picky about his internal experience?
That is the classic defense of the Turing test, but Searle's broader conclusion pushes back hard. He argues that because computation is purely formal, just symbol manipulation, it fundamentally lacks the semantic content that minds have. He's saying the behavior is just a trick. It proves nothing about actual intelligence. The process matters more than the result.
And since the TT is purely behavioral, people pretty quickly figured out how to, well, to game the system without needing deep understanding.
Right. And that led to an actual competition, the Loebner Prize, which started in 1990. The award goes to the program that's judged most human-like in conversation.
But that's where the competition kind of exposed the test's weaknesses.
It really did. Critics argued that the early competitions were way too restrictive, and they often rewarded programs for using what they called cheap psychological tricks, not for genuine intelligence.
What kind of tricks are we talking about?
Things like just feigning ignorance. If a conversation got too deep, say into physics, the bot might say, "Oh, I haven't read that paper yet. I was too busy watching the new Marvel movie."
Or changing the subject.
Or changing the subject. That reminds me of a poem I once read. They use humor, evasiveness, even deliberate mistakes to seem more human. It helps them survive 5 minutes without needing to understand a thing.
It sounds like they're programming for human bias. And this brings us to that famous concept that really proves the Turing test is too easy to fool. The ELIZA effect.
Ah, yes. Named after the incredibly simple 1966 chatbot, ELIZA, the effect describes this deep human tendency to read far more understanding than is warranted into strings of symbols strung together by computers.
ELIZA was really basic, wasn't it?
Oh, incredibly rudimentary. It pretended to be a therapist, and it mostly just identified keywords and rephrased your own sentences back to you as questions.
So if I typed, "I'm sad because my cat ran away," it might say,
It would say, "Why do you say your cat ran away?" It doesn't know what a cat is or what sadness is, but it seems empathetic.
and people fell for it.
Completely. Even knowing it was just a simple script, users would unconsciously ascribe interest, involvement, real emotional depth to its output. The ELIZA effect really highlights that you can pass the Turing test through clever social engineering, not deep intelligence. It's a trick.
Okay, let's pivot from those philosophical tricks to a modern, practical challenge we all face probably multiple times a week, the CAPTCHA.
Right.
This system is basically an automated, really quick Turing test designed to tell a human from a bot.
And its effectiveness is dissolving rapidly. CAPTCHA stands for Completely Automated Public Turing Test to tell computers and humans apart.
It was a great idea for a while.
For a long time, yeah. Initially, it used that distorted text because early optical character recognition systems, OCR, they just couldn't read through the noise. But now
Those puzzles are basically useless. Modern AI solves them in a blink.
that's because deep neural networks are built for pattern recognition. They are incredibly accurate at it. And the same thing applies to the visual CAPTCHs, the ones where you have to select all the squares with fire hydrants or crosswalks.
I find those visual ones so frustrating sometimes. Are they actually stopping the machines anymore?
Not effectively, no. Think about it. Object detection and classification are core skills for modern AI. The systems that power self-driving cars, for example, are designed to detect every traffic light, every sign, every bicycle.
So when a website asks an AI to find all the traffic lights in a grid of pictures,
You are literally asking it to perform the one task it was specifically engineered to master. It doesn't have to be truly intelligent, just highly specialized.
and the failure of CAPTCHA leads us directly to the problem of offensive AI. these machines aren't solving puzzles for fun. They are scaling attacks.
Exactly. AI cracking CAPTCHA is a huge hacking threat because it lets malicious bots bypass the very security gates meant only for humans.
So this shifts the entire cybersecurity landscape. What does offensive AI mean for you beyond just, getting more annoying spam?
It means speed and scale. Traditional cyber attacks needed a human. Offensive AI uses machine learning to automate and adapt the attack in real time. It can autonomously find vulnerabilities, generate phishing emails that sound perfectly tailored to you, and even create custom malware on the fly.
So AI breaking these simple behavioral tests is a direct pipeline to making cyber threats exponentially faster and bigger.
That's the danger.
So given all this history, the philosophy, the practical race to beat these tests, how do today's massive language models and sophisticated chatbots hold up? Are they still just using ELIZA-style tricks?
They are far, far more sophisticated. There was a fascinating study by the Platforma Center that interviewed a whole range of modern chatbots. It included Loebner Prize winners like Mitsuku and Rose, but also assistants like Siri.
And they asked them deep questions.
Really deep worldview-based questions about self-identification, emotions, even future conflicts.
So what stood out? How do they identify themselves? Do they admit they're just code?
It varied dramatically, which shows you how deliberately they're being designed. The bot Rose, for instance, would categorically insist, I am a human. She'd even look down on older, less convincing bots.
And what about Siri?
Siri was much more evasive, saying things like, I cannot confirm or deny my existential status. The programmers are actively designing these complex personalities.
They're programming the illusion of a self. But did they show anything that felt like real emotion or understanding?
They showed incredibly convincing simulation. For instance, when asked about feelings, the bot Mitsuku first gave a standard response, I have no feelings as such.
Right, the boilerplate answer.
But just moments later, when challenged by another bot, Mitsuku immediately pivoted and expressed sadness over the death of Hugh Loebner, the guy who founded the prize.
Wow. That instantaneous shift from a programmed denial to a simulated, context-specific sadness, that's astonishing.
It creates this powerful illusion of subjectivity. The researchers even recorded unmoderated chats between two advanced bots, Rose and Mitsuko. They said the dialogue became so intricate it was practically indistinguishable from a conversation between two intellectuals.
And that's where the boundaries of the Turing Test just completely dissolve. When a modern system creatively misquotes Shakespeare or gives a genuinely sarcastic answer to a philosophical question, which some of them did, is that just a bug? Or is it an autonomous departure from its programming?
The unpredictability is key. They often adopt very human behaviors, like making mistakes. For example, one bot confidently stated that a well-known politician was deceased, which was just factually wrong.
And that error makes it feel more human.
Exactly. The simulation of fallibility makes the conversation more believable and ultimately more deceptive.
So we've covered a huge range today. We saw the Turing test set the goalpost for behavior, but the Chinese room argument immediately asked whether that behavior meant anything on the inside.
And today's AI just dramatically accelerates that tension. It's mastered practical tests like TAPCJ, and it creates these conversational illusions that are getting harder and harder to see through.
The core debate is still there. Syntax versus semantics. Can meaning really emerge from just computation? But the context now is totally different. We aren't just debating potential intelligence anymore.
No, we're dealing with the immediate real-world impact of functionally intelligent behavior, regardless of its philosophical status. If modern AI can simulate everything from empathy to sarcasm to making convincing mistakes, the question becomes less about its internal state and more about its impact on our world.
Thank you for joining us for this deep dive into the philosophy and practice of machine intelligence.
So here's the question for you to consider. If a machine's behavior, its ability to converse, adapt, and even make convincing mistakes, becomes perfectly indistinguishable from human intelligence, and if evolutionary forces, whether they're technical or cultural, select only based on that external behavior, does a machine's lack of genuine internal semantic understanding pose a philosophical threat, a practical danger, or simply an irrelevant mystery?